welcome to ML Down. So, neural networks, training them could be a little bit difficult in terms of understanding what's happening behind the scene. Specifically, if you think about more complicated neural networks like convolutional neural networks, RNNs, LSTMs. I would argue that the main problem that some people find them difficult to understand is because they haven't spent as much time as necessary to understand the simpler neural networks and their training process. Because of that, today I'm going to talk to you about one of the most fundamental methods of training that is called the Perceptron Training Rule, that is used specifically to train a perceptron. And as we talked in the previous video about the perceptrons, a perceptron is the simplest type of neural network. So if you think about it, this is our perceptron. We've got the input vector x, and for every element of x, you've got a weight associated. They will all be linearly combined together and then summed together. So this would be the linear combination. And then this whole thing will go through this sort of thresholding function. And then if this summation wixi is positive, the ultimate output, which we show with O, of this perceptron is +1, otherwise it's -1. And the whole learning task is to learn these weights. The whole purpose is to learn those weights. So that for the data points that you have in your data set, you would like to produce +1 for the data points that belong to the positive class and -1 for the data points that belong to the negative class. Yeah? So far so good. So how can I learn the weights that would result in the correct +1 and -1 for our training set? And that is the whole challenge in the Perceptron Training Rule. Before I continue, there are two main solutions for training a perceptron, and in particular, I mean, more generally, you could say training a neural network. One is the Perceptron Training Rule, which we're going to discuss today, but the more general and stronger one that is all about backpropagation, about gradient descent, all those fancy words that you might have heard, that they will fall under the second category called the Delta Rule that we're going to talk about later. And if you understand these main concepts, you will be able to understand the training process of more complicated neural networks, trust me, much easier. Now, the Perceptron Training Rule. Imagine that you've got your perceptron, and you would start the weights of your perceptron randomly, absolutely randomly. And then you would feed your training data, right? So let's say X, this capital X, is your whole training set, and W is the weights in your perceptron. So you first initialize the weights of your perceptron randomly. And then, for as many times as necessary, you will do the following. For each training example in your data set, let's show that with small x, you compute the output of your neural network, which is the same as O that we showed in our figure. Now, if this O is correct, meaning that, for example, if the actual label of your of that particular training example X is +1, and if the output O is also +1, it means that your classifier believes that that training data belongs to the positive class. When the classification is correct, you will not change your weights. You have initialized them randomly, but you will not change them because your perceptron is currently classifying your this particular training example correctly. Then you would go to the next training example. Let's say that training example belongs to the negative class, but your perceptron produces +1 with that. You would have liked it to actually output -1, but it failed to do so. So it means that you need to modify the weights of your perceptron. so that it would generate the right value for this particular training example. Now, the training rule that we talk about is basically very simple. Wi equals to Wi plus delta Wi. So basically you could say that an easier way to understand this is you could say that the new Wi is equal to the old Wi plus some little tweak, some little change in Wi. Remember, Wi is the associated weight to xi. For example, W2 here is the associated weight for x2. Okay? Remember that this whole thing, this whole vector is your small x. Is one training example that has n dimensions, and every dimension has a weight. So these weights typically, you could think of them as some sort of emphasis as to how important each one of these dimensions of this particular training example is. And after your network converges, then these weights will be fixed, and you're not going to change them anymore. So how should we find this delta Wi, this little tweak? How should we know that? Should we increase Wi? Should we decrease Wi? Depending on the output that our perceptron has produced. So delta Wi is computed as following. This is actually the actual perceptron training rule. It has a few components here. One is eta. We also call this the learning rate. You can think of this as the step size. I'm going to explain to you what that is in a minute. Think of T as your actual ground truth. Let's say it is the truth. And think of O as your output, as we've talked about before. So output could be either +1 or -1. Your ground truth is also +1 or -1, because these are the only values that you can produce with your perceptron. It can either produce +1 or -1. There's no 0.5. There's no -0.5. Okay, because of that, you would like your perceptron to represent the two classes in your training set with +1 and -1, and that is why you use the ground truth of +1 and -1 to label each one of these training examples, so that you would have an indication as to which class each training example belongs to. Okay, and x of I is the ith dimension, let's say ith dim of small x. So that is the ith dimension of your input vector, or your training example, one training example, x. Okay, now let's think about it. T minus OXI, in short, I'm going to explain in more detail, is how much you're going to change. It will tell you how much you have to change your Wi. That learning rate over there, it just makes sure that the change that you will make to your Wi is not too aggressive. Like, for example, if we somehow magically learn from T minus OXI that we have to increase Wi, you would multiply that by this learning rate. And learning rate tends to be a very small value. I'm talking 0.001, 0.0001. So that it would break that huge update in your Wi, so that the change that you will make in your Wi, whether you want to increase it or decrease it, so that that change will not be too drastic. Okay? And this update will happen every time your perceptron fails to classify a particular X in your training set. And that is when you change, you basically modify all the weights in your perceptron according to this rule. Now, let's dig more into detail. What happens if the prediction of your perceptron is correct? Obviously, it means that you don't need to change the weights of your neural network. And that is exactly how our perceptron training rule is operating. Because when the prediction is correct, it means that if the ground truth of your training example is +1, you have produced +1. And if the ground truth of your perceptron of the training example is -1, it means that your O, the output of your perceptron, is also -1. So T equals O, and then this whole expression will zero out, and then your delta Wi would be exactly equal to 0. So you don't need to update anything. And this makes sense, and our perceptron training rule is also following that rule. Now, what if, let's say the output of your perceptron, let's say that is -1, meaning that the perceptron believes that this particular data point belongs to the negative class. But let's say the actual ground truth is +1, meaning that we know that this X belongs to the positive class. What would happen then? This means that the output of your neural network, the weights that you have chosen in your neural network, if you think about it in here, it means that these weights that you have currently in your neural network, when you sum them, multiply and sum them across all the input dimensions, it means that this value was smaller than 0, and that is why the perceptron outputted -1. Now, we know that the ground truth is +1. How should we change the weights of this perceptron so that the output would get closer to 1? How? It means that we have to change the weights in a way that this quantity becomes bigger than 0. Because if that is bigger than 0, only then the output will be 1, right? So this means that you have to change the weights accordingly to make this happen. So we need to increase the weights, basically, to make sure Wixi across all the dimension becomes a larger value so that your output would become +1, okay? So when we want to push the output of our neural network towards a larger value, namely +1, it means that we have to manipulate Wixi, right? This would be the value Wixi that we have to manipulate. We want to make sure that the W's will change in such a way that this quantity would be bigger than 0, so that after thresholding it with our step function, we would get a +1. Yeah. Now, if x's of I were positive, let's say all of them are positive, then how can we increase this quantity? The only way is to do that is to increase Wi's. Makes sense, right? Because x of I, all of them are positive. So how can I increase Wixi when all the xi's are positive? You have to increase Wi, every Wi. You have to increase them so that the whole thing would become positive. Let's see whether our training rule would follow this logic. Let's see whether the delta Wi is indeed positive or not. So meaning that we would like to see this rule to increase Wi. Let's see if it happens. Now, learning rate is always positive. We know that. Okay, so the learning rate is always positive. It's just a step size. Now, when t is 1 and o is -1, t minus o becomes 1 minus -1, which is 2. Again, this one is positive as well. Now, we know that if x of I is positive, this means that this element is positive, this element is positive, this element is positive. Then delta Wi becomes positive. Remember, delta Wi is how much should I change Wi. Okay? And as we discussed just right now, we want to increase WI, right? And that is exactly what our rule is suggesting. Delta WI is positive. And because we're saying that the update rule of my W is the new WI equals the old WI plus delta WI, and because delta WI is positive, it's as if I'm increasing my WI. So if I increase my WI, I will increase WI x of I, and then this whole quantity will become positive, and then the output of my neural network, instead of -1, becomes +1. Thus, I'm getting closer to my ground truth, t +1. Okay? Now, what if our output was +1, but the ground truth was -1? What would happen then? Let's say my x's are positive again. Yeah? In this case, logically speaking, you would like to do something to the weights that would reduce the output of your neural network, meaning that you would like to decrease Wix of I and make it smaller than 0, so that after putting it into the threshold function, you would get a -1 and be the same as your ground truth t. So you want to decrease your Wix of I. Now, if x of I is positive, let's see what happens. So again, the learning rate is positive. T minus O, t is -1 and O is 1. So that would be -1 -1, which becomes a negative value. And x of I, let's say, is positive. Let's say our input has a positive value. So in this case, this one is positive, x of I. T minus O is negative, and learning rate, as always, is positive. So this whole multiplication would be something smaller than 0. So delta WI is smaller than 0. Now this exactly follows our intuition, doesn't it? So you want to decrease Wix of I to make O as close as possible to -1. And if all the x's are positive, if all of these x's are positive, in order to decrease Wix of I, you need to decrease every one of those WI's. Okay? And because delta WI is negative, in our update rule, over here, we say that WI equals WI plus delta WI. So the new value of WI equals the previous value of the WI plus a negative value, which means actually you are decreasing the WI, just so you would make the output of your neural network closer to the ground truth, which in this case is -1. So I hope that this has been informative for you. Today we just discussed the Perceptron Training Rule. That's an important rule, and I would appreciate it if you guys would pay more attention to this particular rule, because this would be sort of fundamental to understanding the training process of complicated neural networks. In the next video, we will talk about the delta rule, gradient descent, and what it really means. I'm posting the link to the blog post of all of these information in the description of this video. Make sure to follow us on Twitter, LinkedIn, Facebook, and you also see the website link. So I hope that this has been informative for you, and if you have any questions, please just post them in the comment section. I'll be more than merrier to answer your questions. So until then, on behalf of Emeldan, take care of yourselves. Bye.